Hello, everyone, and thank you for joining me today. My name's Steve Abraham. I'm a Principal Solutions Architect with AWS, and today we're going to talk about how you can build scalable and reliable enterprise apps with AWS relational databases. So let's first take a look at enterprise apps and what they are these days. So enterprise apps, they have changed a lot, and at the same time, they've remained the same. As many of you are no doubt familiar, there are a number of ISV applications out there that you've purchased for your business and worked with within your business. And then, of course, there are also homegrown apps, right? And so those homegrown apps actually introduce all kinds of different requirements on databases. We have a few examples of some of these applications listed up top between the ERP, CRM, HCM, SFA, supply chain, etc. And of course, e-commerce. Those are prolific across the globe, e-commerce websites everywhere. And then, of course, those requirements, they vary too in scale and performance. I mean, you might have a small internal application that just runs batch reports, say once a month or something like that, or you may have a global e-commerce store online that requires massive sharding and scale and distribution across the globe. High availability and disaster recovery, these requirements also, of course, vary from customer to customer. Again, like I said, you might have development databases where it's sufficient to just have a backup once a night, capture the day's changes, right? Or you might have, that super highly available website online that runs 24/7, and it's absolutely mission critical that it's not only highly available, but also that you have plans for disaster recovery. What happens if a natural disaster were to affect the data center or the region where you're operating? And then security and compliance too. These, of course, are critical for all kinds of applications. And today, a lot of businesses, they rely on old guard commercial databases for enterprise applications. And while these old guard commercial databases work well generally, there are some drawbacks. First, of course, would be that they're oftentimes very expensive, right? You want to launch a new application, you have a new idea, and so one of the first things you have to do if you want to use one of these databases is go out and buy licenses. Those licenses are expensive. Maybe you decide you don't need that database. You've already sunk the cost into buying a license. And so, that can be problematic, right? They're proprietary, and while a lot of these engines have great features, the more of those features that you leverage a lot of times, the more you get sort of locked in, which is really the third thing here too. If you use some of these great features of some of these different engines, then it's very difficult if you decide at some point later that maybe you don't want to pay those large licensing costs, which brings us to the punitive licensing as well, and also ties into, that dreaded audit email where somebody wants to come and audit your licensing environment, right? So all these things can be very problematic. And so because of that, a lot of customers are moving to open source databases. But when customers move to open source databases like MySQL, Postgres, MariaDB, they still want that commercial grade performance and reliability, right? And so even though these things are, you're capable of doing these things with these databases, sometimes they do require a lot of skill. They require a lot of management, a lot of heavy lifting. And, there are certain limits to some of these engines. And so that's why with AWS, we've come out with a better way forward, right? An opportunity to modernize your enterprise applications with Amazon Aurora. So some of you may be familiar with Aurora already. Some of you maybe not. And so, what is Aurora, right? It's delivered as a managed service. What that means is that there are certain things that you need to do to maintain a database. You need to take backups. You need to provide that high availability, disaster recovery like we touched on earlier. You need to do patching. These sort of things that are required for business continuity, and they're critical for business, but they don't actually add any additional value to the business, right? And so with Aurora being a managed service, what we do is we actually take on that burden for you so that you can focus on more important things. And so since we've decided that we want to do this as a managed service, we also recognize, from a couple of slides ago, that if you're coming from a commercial engine world, that you're going to have certain expectations about speed and availability of those high-end commercial databases. And so we want to make sure that we can meet that same threshold or maybe even exceed it. The simplicity and cost effectiveness of open source databases, from what we were just talking about a second ago. If you want to spin up a new database because you've got a new idea about an application that you want to build, you don't want to have to go out and sink money into buying a license right out of the gate just so that you can try out an idea. We want to eliminate that licensing that is normally associated with these commercial databases. Drop-in compatibility with MySQL and Postgres. So this, I think, is very powerful because when we created Aurora, we certainly could have, created a new query language. It could be API driven. It could be all kinds of different things. But one of the key design considerations was we wanted to make it easy for customers that are already using MySQL or Postgres to be able to move those applications right over without having to make any code changes. And so with Aurora, both MySQL and Postgres, they are what we call wire compatible with those engines. That means that if you have an application today that runs on, say, MySQL, for example, and you move the data and the database into Aurora MySQL and change the connection string, your application will not know the difference. Everything at the application level remains the same. The other thing that this allows you to do is if you have expertise on your staff around these engines, MySQL or Postgres, you can leverage that for performance tuning. We've already talked about how you don't really have to worry about backups and high availability and things like that because it's a managed service. And so that does allow you that time to focus on performance tuning and building new features and other things that do add actual value to your business. And the last thing on this list is simple pay-as-you-go pricing. So again, along with buying licenses, if you have an idea for a new application and you want to roll it out, in the old world, you would have to buy hardware. And then you would, of course, have to rack it, stack it, have it delivered. That is not only a lot of expense up front, but it also can take a considerable amount of time. With Aurora being, built into AWS and part of the cloud, you're able to spin up an Aurora cluster in a matter of minutes, use it for as long as you like, and then with no risk, you can simply terminate that cluster as you see fit, and you only pay for the time and the resources that you have consumed. Some of the specific innovations that came with the advent of Aurora was a scale-out distributed multi-tenant design. And in the next slide, we're going to get into a little bit of the details about how this all works together. But for right now, understand that with your storage, it's actually spanned across 3 different availability zones, and it's built to handle any type of scale from a storage perspective. And it also is designed in such a way that it makes it very easy to add additional read capacity and soon to be additional write capacity by way of Aurora Multi-Master. It's a service-oriented architecture, and we leverage AWS services. So for example, Aurora itself leverages other AWS services. For example, the compute nodes are actually EC2 nodes. So we actually use EC2 for the compute resource, right? S3 is integral to the backup strategy for Amazon Aurora, for example. So we leverage these different services that already exist in some of the power of the AWS platform without having to reinvent the wheel. Like I mentioned earlier, we automate administrative tasks. It's a fully managed service. That means that when you specify that when you create an Aurora cluster and you specify how long you want to keep backups, anywhere from 0 up to 35 days, with the default being 7 days, you can do a restore to a point in time anywhere from about 5 minutes ago up to that threshold that you have defined. And in addition, if you want to have multi-availability zone high availability, it's as simple as checking a checkbox, and we handle all of the rest for you. And mission-critical features like global database, parallel query, and serverless, which we're going to get into in a little more detail later on in this session. So, like I said, we're going to, take a look at what is the scale-out distributed architecture that we're referring to when we talk about Aurora. And so if you look at this picture that's on the right, and you imagine that this picture represents a single region, we'll call it, for example, US East 1, right? In that region, we have this shared storage volume that spans 3 different availability zones. And just to refresh everyone's memory, if you're not familiar, an availability zone, you can think of logically, conceptually, as a data center. In practice, there are oftentimes multiple data centers, but what makes one availability zone different from another is that they're isolated from one another in such a way that if there was some type of a network issue or a power issue or some type of natural disaster that would impact a certain availability zone, it's highly unlikely that it would have any impact on the remaining availability zones. And so a lot of AWS services are designed in such a way that they can withstand the loss of one or even greater than that availability zones in a given region. And Aurora is no exception. With Aurora, we span your storage volume across all 3 availability zones within a given region. And when you look at the little squares that are underneath, the little gray and magenta and red and yellow, those are actually storage nodes. And so what happens, if you look at the picture to the left where it says availability zone 1, if you imagine that that is the writer node, and you have performed, for example, an insert, then what happens when you do an insert on a relational database? Well, a few things, but one of the things that is a requirement is that we have to write that to a transaction log, or in MySQL, it would be known as the redo log, for example. Well, what happens with Aurora is we take that redo log entry and we send it out to those 6 different storage nodes that are in the 3 different availability zones. We have a 4 out of 6 write quorum, which means that when 4 of those 6 storage nodes have received it and durably stored it to their directly attached NVMe storage, that's when we consider that write, that disk write, to be complete, right? And so what this allows us to do is, like I said, it gives us that high availability because we have 6 different copies of your data in 3 different availability zones. And we can actually lose an entire availability zone without your application even missing a beat. In addition to this, if you look at these, the different colored nodes down there, you'll notice the red, magenta, and yellow. Each of those represent what we call a protection group. And a protection group is a 10 gigabyte segment. So imagine that you create a new Aurora cluster with no data in it, and you write your first byte of data. We will then, assign 6 of these storage nodes for you to write to. And so you'll continue to write, and once you reach 10 gigabytes plus 1, then we create a new protection group, which means allocating an additional 6 storage nodes. So in this case, we're looking at a volume that has 3 different protection groups, and therefore it has 3 times 6, a total of 18 storage nodes. And so if your volume is sufficiently large, you may have literally hundreds or thousands of these storage nodes that underpin your particular cluster. And so that's something that's sort of a baseline to consider as we move forward through this talk, so that you kind of understand, what those storage nodes are. It's also worth noting that those storage nodes themselves are compute resources. They have a significant amount of CPU and memory attached to them as well. If you look at this picture too, you'll notice that we have these other nodes that are in availability zone 2 and 3. With these, you'll note that they're all reading from the same storage layer, which means that when you perform a write to that storage layer, if one of those readers needs to read a page off the disk, they're reading from the same logical disk as what the writer is writing to. And what this means in practical terms is that your replication latency from the master to the readers is measured in around 10 to 20 milliseconds, largely independent of what that throughput is, if you have a high degree of throughput. And so this allows you to have very low latency readers that are directly attached. It also allows you to do things like spin up and spin down different readers very quickly. If you think about how powerful this is, you think about MySQL as an example. If you wanted to create a read replica in MySQL, how would you do that? You would need to create a bin log replica, and that would involve creating a backup, a copy, a restore, and then streaming bin logs from that master to the reader until it was synchronized. Depending on how much data you have in your database, that could take hours, days. I mean, it's hard to tell, right? With Aurora, when you create a reader, there is no copying of data. There's no persistent data on any of these compute nodes. Instead, all of the nodes, the readers and the writer, are all simply compute heads that attach to that same storage volume. And so when you add those readers, they are able to start reading data nearly as soon as they come online. So even if you had a 64 terabyte volume, you could create a reader and start performing reads within a handful of minutes. Right, so very powerful stuff. Like I mentioned earlier, we do leverage the cloud ecosystem inside of Aurora. We're not only using AWS to create Aurora by way of EC2 and S3 for backups, but we also integrate into those. For example, AWS Lambda, you're able from Aurora MySQL to invoke Lambda functions. Why might this be useful? One use case is perhaps you have a trigger on a table, and then when rows are written to that table, it invokes a Lambda function and passes some parameters to it. An example that I've actually presented before is it's a lower volume table. Maybe it's a customer feedback table, and so as customers leave feedback, it invokes that Lambda function and then sends off an email to let you know that there's new customer feedback in your database. S3, like I said, backups are stored in S3. When you create snapshots, they're stored in S3. And as you may already be aware, S3 is designed for 11 nines of durability, so very highly durable. The other thing, too, about S3 is that you can actually export data into S3, or you can load data from S3 directly into Aurora. This makes bulk import and export operations very convenient and relatively easy and painless. IAM authentication. IAM stands for Identity and Access Management. And normally, this would refer to how you grant permissions to create, modify, and terminate resources within AWS. So it still applies with Aurora that you would use Identity and Access Management to grant a role or a user or someone the ability to create an Aurora cluster, modify an Aurora cluster, terminate it. But something that's different and unique about Aurora, and actually the MySQL databases that run on RDS, which we'll talk about a little bit later, is that you can authenticate your application into the database itself using IAM authentication. And what this means is that you no longer, for your applications, need to store a username and password. Oftentimes, it's the case with applications that there's a configuration file somewhere, or maybe, God forbid, hard-coded into the application code, or otherwise in plain text stored on a hard drive somewhere, a username and a password to the database. With IAM authentication, you no longer have to use that username and password. It's just managed through the role that's assumed by the instance or container that you're running within AWS. And then, of course, CloudWatch. We upload systems metrics and audit logs to CloudWatch, and that gives you all of the powers of CloudWatch. So not only viewing the metrics, but with CloudWatch logs, we have CloudWatch logs insights, which allow you to actually query the logs, and the ability to attach Lambda functions to CloudWatch logs so that as logs are being pushed into CloudWatch logs, you can be taking proactive measures based on what the content of those logs are. And some of those logs include things like the slow query log, audit logs, and different variety of logs that are all captured within CloudWatch logs. So when we were talking about the managed service component of Aurora, I mentioned some of those things that are necessary for business continuity, but they don't really add any new value. Well, that's what you see here on the right-hand side, the automatic failover, backup and recovery, isolation, security, etc. And so by offloading that onto AWS, that frees up a lot of time for you to focus on schema design, query construction, query optimization. These are the things that will actually drive value for your particular application, and that's where you would want to focus the majority of your efforts rather than those other things that can be handled for you automatically by AWS. We mentioned earlier the idea of disaster recovery, right? And with Aurora in particular, we've already covered, what happens inside of a region. If we were to lose, say, one availability zone, you wouldn't even notice. If we lost an availability zone and then lost another storage node, you still would have quorum. You'd still have a 3 out of 6 read quorum, and we could still reconstruct your data. These are all very, uncommon things. But let's say, for example, there was some catastrophe that really swept through, like a hurricane that would come through perhaps and knock out an entire region. In those scenarios, some customers would like to have disaster recovery contingency plans. And so it's been the case with Aurora MySQL, for example, that you could create what we call a cross-region replica. And under the covers, what we're doing is we're really managing a bin log replication from one region to another region that you have configured and requested. And that's great. We manage that for you. We support up to 5 different cross-region read replicas. So that gives you great coverage for that disaster recovery. But one of the things about bin logs is, for all of their great features, they require computational resources on the compute node, right? And you'll remember that we've pushed a lot of that down to the storage node, a lot of our data management activities down to the storage nodes, right? But with binlog, it still happens up at the compute node. The other thing about binlog is that depending on what the write throughput is, it could, adversely impact your latency. So if you have a very heavy write workload on your writer, then it could be that your reader, your cross-region reader, falls out of sync by minutes, hours, days. I mean, it really depends entirely on the application and the patterns. So to address that, we actually decided to innovate again and released at reInvent last year, Aurora Global Database. And what this is physical replication that happens at the storage layer. Now, we still support the cross-region read replicas that use the binlog replication, because a number of customers still like that. They prefer that. They feel comfortable with that. For whatever reason, they would like to use that, and we still support it. But for a lot of customers, they really see the great value in global databases because it allows up to 150,000 writes per second with a negligible performance impact. Because with this, we're not generating bin logs anymore. There are no more bin logs, which means we're not consuming those compute resources on either the writer or the reader. Low replica lag. So even under heavy load, the cross-region replica is on average less than 1 second behind the writer. So that's pretty phenomenal. I would suggest that we can have a system where we have a cross-region replica with less than 1 second RPO, recovery point objective, right? And then fast recovery, less than 1 minute to accept the full read-write workloads after a region failure. So our RTO, recovery time objective, is now ballpark, we'll just call it 1 second for RPO, 1 minute for RTO. Very powerful. We offload that workload off of the compute nodes, bring it down to the storage node. And the way that it works, if you look at this picture here, is that in region 1, we have the 3 availability zones. The master is writing to all of the shared storage nodes, right? The 6 different storage nodes, and still our 4 out of 6. But with this, we actually are going to then take and write out to a replication fleet. That replication fleet is a single endpoint that is highly available, highly durable, right? And it will receive a copy of that redo log, and it will send it across the wire to the other region. And the other region, that replication fleet will receive it, and then it will play those back across the shared storage volume in the other region. And so it's effectively performing the same type of write as what happened in the first region. So pretty powerful stuff. So let's talk about some of our customers that have benefited from some of these different technical innovations that we've released recently. Intuit, many of you have likely heard of Intuit and some of their bigger products like TurboTax, QuickBooks, Mint, and others. They actually were looking for a disaster recovery solution that would look something similar to what we have with global databases, right? And so they were able to actually migrate their commerce platform to Aurora MySQL using Aurora Global Database, and they now have a coast-to-coast disaster recovery solution with that, 1 minute RTO, 1 second RPO, right? So very powerful with one of our customers here. The next thing I want to talk about is Aurora Parallel Query. So Parallel Query, you remember I mentioned that, each of these storage nodes, not only do they have the data stored locally on directly attached NVMe storage, but they also have significant compute and memory, right? So a lot of processors, a lot of memory. And so what we do with Parallel Query is that when a query comes in on a Parallel Query enabled cluster, if it meets certain criteria based on the optimizer, or if you've provided the hint for it and it would benefit from it, we push the query predicate down to the storage nodes themselves. And if you recall, I said that you may have hundreds or thousands of these storage nodes. And so what they do is they take and they will look at the data that they have locally stored on their individual storage node that they're reading very quickly, directly attached to NVMe storage. They are reducing that data, right? They're applying where clauses, they're grouping, other things like that to reduce the data rather than stream all of the data across the wire to be analyzed by the compute node. And then they roll it up, back up to the storage node or to the compute node that initiated the query. For those of you that are familiar with MapReduce, it's very similar conceptually to MapReduce. It's also very similar to how some other databases like Redshift, for example, work. Not the same, but very similar. But because of this distributed nature, Aurora Storage does have thousands of CPUs and tens of thousands of cores that it has access to. And then, pushing that down and parallelizing that query can result in dramatic performance improvements. So let's take a look at what that looks like. This right here are the results of a performance test on a well-known decision support benchmark, right? And you can see that for the peak performance, we were at around 120 times faster with Aurora Parallel Query than we would be without it. And then 8 out of 22 of those queries had better than a 10-fold speed increase. So again, very powerful. And so with that, Netflix, another one of our customers, was able to leverage Parallel Query, and they were able to use it for their hybrid transactional analytical processing database. So, many of you no doubt are familiar with, a lot of databases are OLTP, right? They're high volume, high throughput, singleton type transactions where you're looking up or inserting or modifying a single row or maybe, a small set of rows, but very high throughput, high volume. And then you've got, the OLAP or, the analytical processing type of queries that are far fewer in nature, maybe measured in the tens or even hundreds, but they scan large swaths of data. That's really where Parallel Query, it's one of the sweet spots for Parallel Query is those types of workloads. So this hybrid or HTAP type of in-between workload where you're running OLTP type transactions but still need to occasionally run analytical type queries, that's what really benefits from using something like parallel query. And you can see, what Intuit said. I'll just go ahead and read. We were able to test Aurora's parallel query feature, and the performance gains were very good. To be specific, we were able to reduce the instance type from an R3 8 extra large to an R3 2 extra large. For this use case, parallel query was a great win for us. They were able to reduce their compute to a quarter of what it was before by leveraging parallel query. Aurora Serverless. This is another key innovation that we mentioned earlier. Aurora Serverless is great for infrequently used applications, maybe like a low-volume blog site, or applications with a variable load, even development workloads, right? What this is the same exact Aurora that we've been talking about this whole time, with the key difference, and that is a managed proxy layer that sits between the application and the database instances. And it allows us to automatically scale your compute up or down based on actual demand on the database. And another thing that's really great about it and very powerful for development workloads is it allows you to scale down to 0. So let's say that you're using Aurora Serverless for your development environment, and all day long people are writing code, writing queries, keeping in mind that it's the same Aurora that they're running in production on provisioned Aurora. And then at the end of the day, everybody goes home. So 5 o'clock, everybody leaves. You can configure Aurora Serverless to, if there's no activity, to automatically spin down to 0 compute after a timeout. Let's say we set it to an hour. There are no queries in the system for an hour, and it brings it down to 0. And so we're not paying for that compute overnight while nobody is using the system. In the morning, when the developers come back in and the first person goes to connect, just through normal means, you don't have to know any API calls or use the console or anything. You just go to connect. That very first call, it takes about 10, 15 seconds. But then after that, it's up and running and everything functions and works as though it had been on all day long. But again, you've saved significant costs by not having it run all night. This here, like I said, it's the application. It sends the request to the request router. We scale the database capacity. It's the same storage. So you still get that same six copies of your data, and it's still highly available, highly durable, right? NTT Docomo, they actually are leveraging Aurora Serverless for their development environment. And so, I'll just go ahead and read you here what they had to say. It's that it'll allow NTT Docomo to reduce operational costs by matching capacity to actual demand, because developers can use Aurora Serverless just like traditional MySQL database. It will be easy to adopt in our service infrastructure. So very easy to adopt. It's the same Aurora that you've been using. It just has that ability to automatically scale up and down to 0 if you request that. So why are customers moving to Aurora? We talked about customers using those open source engines, but they want to get, the performance of a commercial database engine, right? And so with Aurora, we get about 3 to 5 times the throughput, the query throughput, that we would out of the similar open source engines, for the same size amount of compute. There's better availability and durability because of the storage layer that we discussed earlier. Reduces cost up to 60%. We've talked about features like Aurora Serverless that allows you to, scale that compute to 0. Something that we kind of glossed over, but I think is very powerful with regard to cost too, is storage. If you have an Aurora cluster, you only pay for 1 copy of the data. So if you have that storage and you have, say, 10 terabytes of data on there, as you create new readers, those readers don't make copies of that data. They're reading they're reading off of the same set of data. So even if you have 15 read replicas, 15 Aurora replicas, you're still only paying for 1 copy of the data. So there is an opportunity to save storage costs there as well. For customers that are using commercial engines, Aurora is about 1/10 of the cost. There are no licenses, which makes it super easy to get started. We integrate with the other AWS services natively. We're comparable performance and availability to some of those commercial engines. And then we also have migration tooling and services to show you, what Amazon.com itself thinks about Aurora. You can see that 90% of Amazon fulfillment centers are running inventory, inbound, picking, sorting, and outbound operations on Aurora. Verizon is another one of our customers that leverage Aurora PostgreSQL, and they needed to do a migration, into PostgreSQL, and they were able to actually leverage the AWS Data Migration Service and Schema Conversion Tool. And those two tools, they allow you to, take, maybe you're running on, a commercial engine today and you want to convert into, as an example, Aurora Postgres or Aurora MySQL. The Schema Conversion Tool will actually do the work, a lot of the work anyway, of converting your commercial schema into an open source schema. And of course, the database migration service will actually move that data from the source into the target, and can also do ongoing replication so that you can do low downtime cutovers, and you can also use the database migration service for other purposes once you're in AWS, maybe for a reporting replica or other similar purposes. So, a better way forward, lift and shift to the cloud with RDS. So a lot of times, maybe you're not ready to move all the way on to Aurora today. Maybe you have a commercial database and you feel comfortable with it. You want to keep that commercial database, or maybe you're just not ready just yet. Maybe you're going to look at moving to open source or Aurora at some point in the future, but you just don't want to do it today. Well, fortunately, we do make it a lot easier for you to do that with using RDS. And we've talked a little bit about this as it pertains to Aurora, but the same thing applies for other engines as well. With RDS, we handle the hardware and software installation, the database configuration, patching and backups, cluster setup, capacity planning, all of that. You can see here that we actually support not only Aurora, which is our own engine, but MySQL, PostgreSQL, MariaDB, SQL Server, and Oracle. So if you're running on any of those engines, you can today move those databases directly into AWS, run them either on EC2, self-managed, that allows you to have full control over everything and allow you to have full availability to do whatever you want to do with the database. But if you want to take advantage of RDS and be able to take advantage of the how we manage the backups, high availability, etc., you can also choose RDS as well. Instacart is another one of our customers, and Instacart actually, they actually turn to AWS to run their database, their Postgres database on RDS. In other words, they already had a database that was running on Postgres, and they said, you know what? We have other things that we need to do. We need to focus on taking care of writing new code for our application, for our business, and we don't really have time to manage all these backups, etc. And so now they're able to add millions of new items to its database every month, and allowing the engineering to improve the customer experience rather than managing ongoing backups. Extended Stay America, they were able to increase their availability, scalability, and reduce their costs by running RDS SQL Server on AWS. So, I know we've talked a lot about, moving away from these commercial databases, but the fact is there are still some customers that are running on them today. Like I said, maybe they just aren't ready just yet. RDS SQL Server still will provide significant value for those customers that want to move on there. You can see the quote here from Extended Stay America is that scaling our e-commerce applications with RDS SQL Server, we saw higher availability, scalability, and we were able to reduce our operational costs by 25%, allowing us to reinvest savings in our core business. So very powerful, right? What about other AWS databases, right? So, one-size databases don't really fit everybody anymore. The relational database has been sort of the Swiss Army knife of databases, and it's been for a variety of reasons. I mean, in some cases, it's just we have a license for this database engine, and so we're going to just use this database engine for this purpose. Or maybe it's what we know. We have expertise in-house around this type of database engine, and so everything just runs out of there. But the reality is that relational databases are great for relational database workloads. They're not always the best for other types of workloads. And so one of the things that we are really focusing on, and a lot of our customers are looking at, is breaking complex applications into smaller pieces and pick the best tool to solve each problem, right? Since we don't have the licensing issue anymore, we don't have to contend with that, and that allows a lot of our customers to experiment with these different types of databases and learn more about them and determine which ones of these databases will make the best tool for what they're actually trying to create. And so this will help to ensure that the apps are well architected and that they scale effectively because they're purpose-built, right? And developers are also building highly distributed apps using a multitude of purpose-built databases. So what are some of these common data categories and use cases? Well, there's relational, and that's what we've been talking about through most of this session today. But there are also key value. Can you do a key value in a relational database? Sure, you can, but you don't need to. It may be a little bit of overkill in some areas because relational databases have features that key values just don't need, and a lot of key value databases can scale a lot easier than a relational database, so maybe it's not even advantageous to use a relational database for that purpose. Document databases, in-memory databases, graph databases, time series, ledger. I won't go into each one of these, but you can see on here what some of the different use cases are for each one of these. And so a lot of times, customers, they see this and they think, well, what does AWS have to offer for each of these? Well, with relational databases, we have RDS, and as we've already discussed, that encompasses Aurora. It encompasses open source, like MySQL, Postgres, and MariaDB, as well as commercial, like Oracle and SQL Server. For key value store, DynamoDB is the go-to oftentimes. DocumentDB has been released recently for document type database workloads. In memory, we have a service called Elasticache. Elasticache is conceptually similar to RDS in that we manage already available open source engines like Redis and Memcached, but it allows you to use those engines for your applications without having to do all of that undifferentiated heavy lifting of maintaining those databases. Neptune is our graph database. TimeStream is our time series database. And of course, QLDB is our ledger database. Let's take another look at another one of our customers. In this case, it's Airbnb, right? Airbnb, they actually moved their main MySQL database to RDS so that they didn't need to manage that undifferentiated heavy lifting of backups and other ongoing maintenance. And then they decided to move some of the data out of MySQL into DynamoDB for some of their key value type lookups, right? And use Elasticache to store cache data between their relational database and their application so that they would have sub-millisecond site rendering. So today, if you want to know how to get started for Amazon Aurora, you can go to aws.amazon.com/RDS/Aurora. For RDS, you can just do aws.amazon.com/RDS. And then we have the URL at the bottom for some of our 10-minute tutorials. I'd like to thank everyone today for your time and have a great day.